Today we are going to discuss the Laplace transform method to solve differential equations, that is initial value problems. So Laplace transform method to solve differential equations. Differential equations. Equations, that is initial value problem. Okay, so consider an initial value problem. Consider an initial value problem y double prime plus a times y prime plus b times y. This is equal to some r times t. So sorry, r of t. Equation number one with the initial conditions. What are the initial conditions? The initial conditions are y0 is equal to k0, k0, and y prime 0. This is equal to k1. So what is an initial value problem? An initial value problem is a differential equation with initial conditions. Okay, so this is a second order differential equation, and these are the initial conditions. Here y are functions of time. So this is the value of y at time t equal to 0, and there is some constant k0, and this is the value of y at this is the value of y prime. There is the derivative of y with respect to t, that is dy by dt. This is dy by dt at time t equal to 0, and that is equal to another constant k2, where here small a and small b are constants. Small a and small b are constants. We are going to solve this initial value problem by using Laplace transforms. Here, this capital R, this can be the given input applied to a mechanical or electrical system, and this yt, this yt is the output, that is the response to the input. I repeat, here this RT can be the given input, that is it is a driving force applied to the mechanical system or electrical system, and this yt is the output which we are going to obtain by using Laplace transform methods. So in Laplace's method, we do 3 steps. We do 3 steps. Okay, step number one. We set up the subsidiary equation, that is setting up the subsidiary equation. And this equation is an algebraic equation for a transform. And this is an algebraic equation for a transform. So if small y is the Laplace transform of capital Y, then we take the Laplace transform of this whole equation. So setting up the subsidiary equation, this is an algebraic equation for the transform obtained by transforming equation 1. By transforming equation 1. Namely, so if I take the Laplace transform of equation 1, what do we get? So first we take the Laplace transform of y double prime. And we saw last time that the Laplace transform of y double prime, this y double prime is s square small y is the Laplace transform of capital Y minus s times the value of capital Y at t equal to 0 minus y prime, the value of y prime at time t equal to 0. I repeat, the Laplace transform of y double prime is s square y minus s capital Y at t equal to 0 and y prime at t equal to 0. So this is the Laplace transform of y double prime. Next, we take the Laplace transform of ay prime. Since a is a constant, we can give it here a. And what is the Laplace transform of y prime? The Laplace transform of y prime is s small y minus the value of capital Y at t equal to 0. This is the Laplace transform of y prime plus b times if I take the Laplace transform of capital Y, I get small y. This is equal to, if I take the Laplace transform of the capital R, I get small r. And small r is a function of s. Okay, where small r of s is the Laplace transform of capital R of t. Okay, now we have obtained the Laplace transform of equation number 1. Now let us collect the terms that contain small y prime. We have one term here, another term here, the third term here. So collecting the y terms, we have the subsidiary equation. And what is the subsidiary equation? The subsidiary equation is, from here we have s square, and we have s square plus as, plus we have b times y. This is equal to, now we have y minus s y0 minus a y0. If I take it towards the right hand side, it becomes s plus a capital Y0 plus y prime 0, right, becomes plus y prime 0 plus this rs. Okay, so in the first step we have obtained the subsidiary equation. Okay, now let us write step number 2. This is next is step 2. What is step 2? The solution of the subsidiary equation by simple algebra. That is solution of the subsidiary equation by algebra, simple algebra. Okay. So if I divide both sides by s square plus as plus b. Okay, so if I divide both sides by s square plus as plus b, what do I get? So we divide by this s square plus as plus b. On both sides we get y. This y, it is a function of small s. This is equal to s plus a times y0 plus y prime 0 divided by s square plus as plus b plus this rs divided by s square plus as plus b. Okay. This is what we obtain in equation number 2. So we solve for y. Okay, and this y is the Laplace transform of capital Y. Okay, next, third step, step number 3. This is step 2. Now let us come to step number 3. Step 3. If I take the inverse Laplace transform of this, I get capital Y. So step number 3 is inversion. Inversion of y to obtain capital Y. Capital Y t. And capital YT is what? This is the inverse Laplace transform of small y. Okay. That is fine. So we can call this equation number 1. Fine. So we reduce equation 1 usually by partial fractions. Usually by partial fractions. Partial fractions to a sum of terms whose inverses can be found. So what is step 3? Step 3 is that we take the inverse Laplace transform of this equation, inverse Laplace transform of this equation, and we obtain capital Y. And how do we usually proceed? We reduce this equation number 1, we reduce equation 1 usually by partial fractions to a sum of terms whose inverses can be found. Okay, this is fine. So let us look at one simple example. Simple example. Solve the differential equation y double prime minus y, this is equal to t, subject to the initial conditions. The value of y at initial time is 1, and the value of y prime at initial time is also 1. So as an example, let us consider this initial value problem. Okay, solution. Let the Laplace transform of capital Y of t be equal to small y of s. Then taking the Laplace transform of the above equation, we get, so when I take the Laplace transform of y double prime, what should I get? I should get s square small y minus s times the value of capital Y at 0 minus y prime at 0. This is the Laplace transform of y double prime. Then minus, we have one minus here, minus Laplace transform of y, Laplace transform of capital Y is small y, and this is equal to, now if I take the Laplace transform of t, the Laplace transform of t is nothing but 1 by s square. Okay, so this is the Laplace transform of the given differential equation. Okay, now let us substitute these values. Y0, that is the initial value of y. It is given that the initial value of y is 1. So this is equal to 1. Similarly, the initial value of y prime is equal to 1. So this is also equal to 1. Okay, so this implies s square minus s minus 1, sorry, s square y minus s minus 1 minus y. This is equal to 1 by s square. Okay. Now I take terms containing y, so I have this term. So s square minus 1 times y, and remaining I take it towards the right. I have s plus 1 by s square. Okay, so from this I solve for y. So this implies y equal to this s plus 1 divided by s square minus 1 plus 1 by s square minus 1. Okay, this s square minus 1, this can be written as s plus 1 whole into s minus 1. So from that s plus 1 will cancel with the numerator. What remains will be 1 by s minus 1. So this is 1 by s minus 1 plus 1 by s square minus 1. This second term, we can use partial fractions, okay, to write it as a sum of two terms. So this is 1 by s minus 1. This is 1 by s minus 1 plus this term. It can be written as a sum of two terms. That is 1 by s square minus 1 minus 1 by s square. This has been reduced to these two terms by using the method of partial fractions. Okay. Let me repeat. 1 by s minus 1 is 1 by s minus 1 here. And this term can be written as a sum of two terms by using the method of partial fractions. So we have obtained y equal to this. Now, let us take the inverse transform. Therefore, capital Y of t will be the inverse Laplace transform of small y. So this is inverse Laplace transform of 1 by s minus 1, okay, plus inverse Laplace transform of 1 by s square minus 1 minus inverse Laplace transform of 1 by s square. Now, the inverse Laplace transform of 1 by s minus 1. This is nothing but e to the power t. Then this plus inverse Laplace transform of 1 by s square minus 1. This is nothing but sine hyperbolic t. And inverse Laplace transform of 1 by s square, this is nothing but t. So the final solution is capital YT is equal to ET, which is the inverse Laplace transform of this. Then sine hyperbolic t, which is the inverse Laplace transform of this, and 1 by s square. The inverse Laplace transform of 1 by s square is t. So this is the final solution. So this is how we solve a given initial value problem by using the method of Laplace transforms. Next, let us look at one application of unit step function. That is shifting a function using unit step function. unit step. Shifting a function using unit step function. Okay, so let capital F of t be 0 for t less than 0. That is, let f of t be a function such that for t less than 0, the function is 0, and for t greater than 0, the function has some form. Okay, then f of t minus a, u of t minus a, with a greater than 0, this is equal to the function ft shifted, that is shifted to the right, by the amount small a. Okay, so suppose the function f of t has some arbitrary shape like this. This is t, this is f of t. Now the same function t, f of t minus a, u of t minus a. If I take f of t minus a and u of t minus a, then this is 0, this is a, then this function is the same function shifted by an amount a towards the right. So this function has been shifted towards the right by an amount equal to a. Okay, so this is how we shift a function using the unit step function. As a simple application of this, we can write the output of a half-wave rectifier. The output of a half-wave rectifier. The output of a half-wave rectifier, if it is given by this expression, this graph, like this. This is 0, this is 2, this is 4, this is 6, this is 8, this is 10, something like this. And this is 12. This is t. Say this amount, this is say 4. This is f of t. Suppose this is the output of a half-wave rectifier. This is 12, this is 14, and so on. This will continue. Then this function f of t can be written in terms of sine and the unit step function in this form. Okay, it can be written as a sum of many unit step functions, like this is 4 sine omega t, this is pi by 2t. Okay, 4 sine pi by 2t times, so this first term 4 sine pi by 2t multiplied by ut, 4 sine pi by 2t ut. This will give us this part plus the other part also. Then minus u of t minus 2. Okay, and what will this give? This will give only this curve, only the first curve, u of t minus 2. This will give only the first half sine wave, plus u of t minus 4. Now if I add this and subtract u of t minus 6. Then what will I get? I will get this first half sine wave from these two terms, and from these two terms I will get the second half sine wave like this, and this will continue so on, and this will continue on. So by using a series of unit step function, I can model the output of a half wave rectifier like this. Okay, so now using this idea, let us write the second shifting theorem. Let us write the second shifting theorem. Second shifting theorem. Second shifting theorem, this is also called time shifting. Time shifting. Time shifting. Okay. So if the Laplace transform of capital F of t, this is written by given by small f of s, then the shifted function, there is tilde f of t. This is given by capital F of t minus a, the unit step function t minus a. This shifted function, this is equal to 0 for t is less than a, and this is equal to f of t minus a for t greater than a. Okay, so if the Laplace transform of capital F of t is small f of s, then we construct the shifted function and we take the Laplace transform of this shifted function. So this shifted function has the transform e to the power minus as f of s. That is the Laplace transform of f of t minus a, u of t minus a. This is e to the power minus as, the Laplace transform of f of t. This is e to the power minus as f of s. This is the second shifting theorem, also called time shifting theorem. Here we have shifted time by an amount equal to a. Okay, so this is the second shifting theorem. So if I take the inverse of both sides, so taking inverse on both sides, we can write f of t minus a, u of t minus a, and this is equal to the inverse Laplace transform of e to the power minus as f of s. Okay, so this is the second shifting theorem. We can compare it with the first shifting theorem. What was the first shifting theorem? Let me write it down here again. The first shifting theorem, we had Laplace transform of e to the power at f of t. This was equal to f of s minus a. This was the first shifting theorem. There was a shift in the s. Here we have a shift in time. Okay, there was a shift in the frequency s. Now we have a shift in the time t. So this is the difference between the first shifting theorem and the second shifting theorem. Okay, as an example, let us consider example find the Laplace transform of Laplace transform of the function f of t equal to e to the power minus a t minus 2 u t minus 2. Okay. So f of t, the given function is this. We have to find the Laplace transform of this given function. We know that here we have shifted the given function by t minus 2. So the unshifted, the original function would be e to the power minus at. Okay, the unshifted original function would be e to the power minus at, and we already know that the Laplace transform of e to the power minus at, this is nothing but 1 by s plus a. From this expression, from the first shifting theorem, we already know that the Laplace transform of e to the power minus at is 1 by s plus a. Therefore, the Laplace transform of e to the power minus a t minus 2 u t minus 2. We apply the second shifting theorem, that would be e to the power minus as times f of s. Here, what is a? A is 2. Okay. So this would be, I repeat, e to the power, here we have t minus a, t minus a. So this would be e to the power minus twice s. E to the power minus twice s, because we have shifted by an amount 2. That 2 should be the coefficient of s, times the Laplace transform of e to the power minus at. That is nothing but e to the power minus twice s divided by the Laplace transform of e to the power minus at is 1 by s plus a. So s plus a. So this is the final answer. This is the required answer for the Laplace transform of this given function. Okay. We can look at another example. Example 2. Find the Laplace transform of the function given by figure, given in the figure. So the figure is something like this. The figure is something like this. Okay. This is 1, this is 2, and this is minus 1, this is 0, this is 1, this is 2, this is 3. Okay. So for values of t from 0 to 2, its value is 2. And from 2, it reduces to 1, and then goes like this. So this is 1, this is 2, this is 3, this is minus 1, this is 1, this is plus 2. Okay. This is the graph of the function. We have plotted f of t on the y-axis and t on the horizontal axis. So here, this is the solution. Here, f of t can be expressed as f of t equal to twice ut. Twice ut means for values of t less than 0, this function is 0. For values of t greater than 0, this function is 2. So this starts from here and it will continue forever. But we want it to jump to -1 at the point t equal to 2. So what should we do? We should subtract 3 times u of t minus 2. Okay. So from t to t plus 2, we have this line. And from t equal to 2, we subtracted 3. So we suddenly jump here, and now we have 3, sorry, -1 here. And this will continue forever. So if we want it to come back to 0 at 3 again, what should we do? We should add another u t minus 3. So now if I add another u t minus 3, then at t equal to 3, I'm adding 1. So -1 plus 1 will be 0, and then it will continue at 0 forever. Okay. So this graph, this figure is given by this expression. And since we know that the Laplace transform of u of t is 1 by s, and therefore Laplace transform of u of t minus 2, this will be e to the power minus twice s by s. And similarly, Laplace transform of u of t minus 3, this would be e of minus 3 by s, minus 3s. Therefore, Laplace transform of f of t, that is this function, should be equal to 1 by s, 2 minus 3 e to the power minus twice s plus e to the power minus 3s. This is the required solution. Let me stop the recording.